So what I want to focus on today is firming up a few things. Not just from the last section we did, the inverse stuff, but from throughout the homework. But first off, any specific questions or general?
There was one where to write the first periodic function in terms of the second.
Where are we at?
Section 6.3.
It's number 39.
Yeah, number 9.
Oh, yeah. So here, tell me, what are the only real identities that we know? We have those definitions of the trig functions themselves, right? I don't include that in identities. Those are the definitions of what they are. What are the only, we know 3 identities really, currently. What are they?
Sine squared.
Hey, all right, there you go.
Sine squared equals 1.
How can you develop another one based off of that? Divide by sine squared, for example. Right? If I divide by sine squared, I get 1. What's cosine squared divided by sine squared? Cotangent squared. And what's 1 divided by sine squared? Cosecant squared, 11, because whatever sine is cosecant. So there's another one. And if I divide by cosine squared, I'll get tan squared plus 1 equals secant squared. Notice how the cos stuff goes together and the non-cos stuff go together in those seconds on the 2 below. Right? Sine and cosine, they like each other a lot. They go together all at the same time. All right. So when they ask you to write, for example, the first one says, write tangent theta in terms of cosine theta. Right? What is tangent theta fundamentally? Sine over cosine. That's tangent theta. Is that tangent theta in terms of cosine? Not really. It's tangent theta in terms of sine and cosine. So what do you want to get rid of or replace? Sine. I don't want sine in there. It says in terms of cosine only, not in terms of sine and cosine. So what can I replace sine with in terms of cosine? Which one of these 3 relates those two? The one that has a minute? Yeah? I like it. So what can I do with this? I want to replace sine. So I want to solve this for sine and then plug it in. Now what happens when you go to solve this for sine? You're going to eventually have to take a square root. There's going to be a plus or minus, but you know which quadrant you're in. Bam. Right? So that's where you come in as a human and go, I know which sign it's going to be based on what quadrant I'm in. You guys see how to attack that kind of problem? Using these identities. These identities, one way to look at them is they are relating different trig functions to each other in a different way. Real quick, look at this first one. What's the definition of sine theta given some triangle? We'll call this y, x, and h. What is sine theta then? Y over h. That's great. And cosine theta would be? That's awesome. So sine squared theta plus cosine squared theta. What's sine again? Sine is y over h. That's y squared over h squared. Cosine is x squared over h squared when you square it. You guys kind of with me here? A little bit? Not really at all? You don't want to tell me? Am I alone? Are you holograms? What's going on? Hello? People? Hey, people, person.
You lost me a while ago, so it's cool.
Shit! Where'd I lose you? Don't let that happen.
Right. I'm catching.
I like that. The minute your pen hit the board, man, you had lost me.
Right.
Shit. All right, so these 3 we've talked about before, right?
This is a problem from the book, the homework.
That problem's done. I'm moving on.
Oh, okay. That's what I was confused.
All right, gotcha. I wanted to go back and explore this a little bit more. I mean, we looked at this in one way and came up with this identity. Now I want to go back and look at it a slightly different way. All right, so we're cool with these 3, right? In fact, these 2 come from this one, so that's the only one I have memorized, really. That's the definition of sine. So now I'm just looking, what is sine squared plus cosine? I just want to look at that. What is it in terms of what I know sine and cosine are? Just what the hell is it? And it's supposed to be 1. So it better freaking come out to be 1. So do these have the same denominator? Yeah, so then I get that's x squared plus y squared over h squared. But what's x squared plus y squared? No. A squared, thank you. From this triangle I've drawn, it's not a unit circle, right? This is whatever the hell this triangle wants to have as a hypotenuse. It can have 1100, right? Whatever it wants to have. So x squared plus y squared is h squared, divided by h squared is freaking 1. So I don't care if I come from the unit circle. We developed this kind of like assuming we were in the unit circle. But I want to show you that this relationship doesn't require that. Sine and cosine will always reduce to the freaking values that we know. So this equation kind of does the same thing. It will reduce to 1 on that side. All right, maybe. All right. Anything else from homework that I can over-explain? Let's just make sure you guys understand. Coming back to this problem, solve this for sine, and you plug it in there. The only thing you really have to do is figure out if it's positive or negative. And they tell you which quadrant it's supposed to be in. So you'll know what tangent it's supposed to be.
What problem was that?
39, yeah. Section 6.3. Yeah.
637.
Oh, yeah, good. All right. If I don't get a question on this problem, I get worried. Have you guys ever done this? Well, first off, have you read this damn problem yet? Number 70? Section 6.3. They got this steel pipe being carried down a hallway. And if it's too long, they are never going to make that turn, right? And this is kind of ignoring 3 dimensions, which you go, thank God it's ignoring 3 dimensions. That would make this really, really disgusting. So we're assuming it's in 2 dimensions, right? So maybe we should say it's like a board, so it takes the 3rd dimension out. And you're like, oh shit. So I remember I got a mattress once, and the mattress would have been fine, but the box spring just did not want to turn the corner up into the attic room I had. I was like, oh shit. I should have probably figured this out earlier. So I just had it sitting down there. I'd have to, if I pushed it this way, I can go up into my room, but it blocked the front door. So if we wanted to leave, I'd push it the other way and block my room door and get out the freaking front door. So, if you've ever done that, it's a normal thing. We're human. We don't really have this in our heads too well. So the whole idea of this problem is, how long can that pipe be so that it'll make that turn, right? Blah, blah, blah. So as it is sitting there currently, really. So here's the turn we're going to try to make. So right now it's like, oh, screw it, Jeff. So it's got a certain length to it. You're not going to be all right, are you? And they give me this is 6 feet. This is 9 feet. Not drawn to scale. And they want you to show, they actually give the answer, they want you to show that this length is dependent on this angle. I like it. All right. So they give you this angle here. And the length of the pipe is, of course, this whole thing. So this whole thing is L. But what kind of naturally happens when I draw this? Because the 9 and the 6 don't really relate to each other. I mean, that's after I've turned the corner. So the 9 and the 6 don't have any direct relationship with each other. Do you guys see that? Because I can push that wall back and that could become more than 6. Right? That would be more than a day's worth of work to push that wall back. But you guys, that's explaining those are not connected. So that kind of sucks. The angle then can't have anything to do with ratios of those two numbers. So what kind of naturally happens with this picture related to trig? What am I always looking for with sines and cosines and secants and stuff? What do I hope shows up visually? Triangles. In fact, specifically, right triangles. Right? That's always nice. Yeah, so are there right triangles? Yes, there's one here. And there's one, if I do this, There. Coolness. Now you could do a couple things. Is this angle inside this triangle? No. And you could either draw this way, or let me do this, because this is actually related to another problem. Can you guys see how to get that angle into this triangle?
Yeah.
How?
90 minus 5.
Yeah, what's this angle here?
90 minus alpha.
90 minus theta. Or alpha, whatever letter you want to use. I like it. And then maybe not 9, maybe 90. I like how everybody's cool with that. 9, sure. 90 minus theta, right? 90 degrees. So this one's got to be... Why is that 90 minus theta? Because that's theta. This whole thing is a right angle there, right? We're assuming that the builders did that. Made the hallway straight, which is always nice. That's bad, so they want to make it straight. So that's 90 minus theta, because the whole thing's 90, that's theta, that must be the rest. Now, of course, that then must be theta, because these two have to make 90, so that overall you get 1/8. I mean, do you guys see how to play with the angles when they're sitting next to each other? You should be able to work it into where you want it. You didn't have to do this on this problem, but there are other problems where you must do that. Okay. Alright, so that's theta. So now I've got this beautiful little right triangle here, right? So how do I get, so this L, this whole L, I can just look at this piece, I'll call this, and remarkably enough, I'll call it L1, just to be remarkably creative. So what trig function can I set up for L1 related to what I know? What trig relates this angle to that side and that side? Sine, kick ass. So sine theta equals
9 over alpha.
Yeah, 9 over L1. And do you see, L1 would equal 9 over sine theta, but what's over sine theta? What's 1 over sine theta? Cosecant. So if you do the same thing we just did there, you're done. All right, that's problem's nowhere near as difficult as it looks when you first get it. You're like, holy shit, how the hell am I supposed to do that? You just got to draw it, realize there's triangles in there, and use them. That's all you got to do. Right. Yeah.
So how is it you got the cosecant? I know it's supposed to be 1 over sine, but where did the 1 over
So I
sine?
solve for L1. I got to multiply it up and divide that down, right? Is that cool? A better way to write 9 divided by sine theta is 9 times cosecant theta.
Okay.
Because 1 over sine theta is cosecant. So that I got that piece. Now where do you think that piece is going to come from? Probably from the second triangle. So it's really just realizing in the picture, noticing where the triangles are, and then attacking them. Right? So since we haven't done 6-5 and 6-6 yet, you're always looking for right triangles, because we only currently know how things work with freaking right triangles. Okay, maybe. You guys seem especially oppressed today, I'm sorry. Shit, you can't even laugh at that one. Alright, okay. I had to go one level deeper. Inception of getting you guys to react. Alright. Okay, so anything else from homework? Yeah.
Can we do 64 from 6.3?
6-3 was our nemesis. Alright. Nemesis. The rain gutter problem. Ooh, yeah. Ooh, I like it. And these kind of problems are kind of funny because you think it's kind of nice when they give you what the answer is going to be, but so often that screws you guys up so bad because the work, it doesn't look like the answer until step 4, and you kind of give up on step 2. That's not looking the way it's supposed to, and I'm like, shit, just keep going. So it kind of almost sucks when they give you the answer. So they want to know what's the area, right? Let's see, blah, blah, blah. They give me this is 10, 10, 10. Very possibly not drawing the scale there. You guys with me? This is 64, right? 6-3, yeah. So they give me this thing. It started off as a straight pipe, and then they bent these sides up by a certain angle. You kind of with me? we've done a problem like that before, but we bent it until it became rectangular. And we did the cross section of that, right? So now we're saying, now we know angle shit, so let's just do it to some certain angle. And get a trapezoid up here. Dude. So a really good thing to remind yourself is what the hell is the formula for the area of a trapezoid. If you don't know that, you can't do this problem. Dude, the back of the book, yeah. I mean, that's what we said before, right? You always look in the front and the back of the math book that you get, just to see what the hell's in there. But real quick, this is a decapitated triangle, right? You guys with me on that? They turn him upside down and then cut his head. Oh, that's horrible. Sorry. And the area of a triangle is 1/2 times the only base times the height. Well, the area of a trapezoid is 1/2 times the sum of the two bases now times the height. It's very similar. And you can draw in, you can make triangles, you can find the areas, you can add them together, and you get this. That's the derivation of that formula. But always remember, it's like a triangle with two bases. So instead of one base, I better have room for two bases in the formula. Right? Very easy way to remember that. Alright, so you got to know this first. So what's really nice then is, what's the only thing I currently know that needs to go into this formula? There's only one thing I know. One base is 10. That's all I know. This is not the height, right? That's slanted. Okay. Blah, 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 blah. What else did they give me? Cool. I like it. So how the hell... So draw in the height. What would it look like if you drew in the height? Why would this not be the height? It's not straight. It's straight according to what? According to the base, right? So when I draw this up, it's got to make a holy shit, which is what we're always wanting. So the minute you draw in the thing you need for this formula, it actually tells you what to do next in the problem, right? So I need to figure out what this height is. And it's the same thing over there, so who cares? I'm not going to draw it. So what I've just created this little triangle, right? I know that this, I think this is how they define it, right? Yeah. This is theta. So again, that problem we just did a minute ago would be helpful. So where's theta go in this triangle? Beautiful, because this would be 90 minus theta, so that must be theta. And now you can write the height in terms of theta and 10 using the correct trig function. I mean, you start to see a lot of these problems are the same. Create a right triangle. Look at what you know. Which trig function relates what you know with what you don't know. Write it. Do it again maybe. So we're equal them. Whatever you got to do. But that's the fundamental idea. What trig function relates what I don't know with what I want to know. Cool. So what would you get there? Do it again. H equals 10 sine theta. I like it. Cool. So that's the height. The height is 10 sine theta. And what else do we not know? Let me go ahead and draw on this other height. We don't know what base 2 is, but we know we can figure out what this is, right? And how will that relate to this? Same damn thing, because they raised it by the same amount on both sides, right? And then what's this? 10 freaking centimeters, because supposedly it's a square in the middle, or a rectangle in the middle. Because these went straight up, especially if you drew them straight, which I just didn't want to. Alright, I've done enough work for you, so you guys can finish that one. That should get you started, at least. I mean, that's pretty far along there. Okay. Alright, anything else from homework? Yeah.
42, 6.4.
Oh, yeah. Alright. This is kind of neat, because when you're at the beach or something and you think about, well, how far am I really looking out? When you see the very edge of the ocean, you know that's not like they thought in the old days. Oh, shit. That's not going to happen. You just kind of keep going around the curve. You're like, how far is that exactly? Right? If I had this huge boat, how far out would it have to go before I lost sight of it? Like it went over the curve according to my eyesight. And then how far up would I have to go to go on a soapbox or something? How much further can I see? So this is really what this is kind of talking about. But now, of course, we're getting crazy. We're going up in a satellite. Blah, 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 blah. Here we go. Cool. So give me this picture here. Satellite dude. Whoa. Okay. So this theta. Alright. Oh yeah, okay, good. So this here is the height above the Earth. This whole thing here would be the arc length. Ooh, all kinds of neat stuff. So if you were here, then the distance you can see in either direction would be related to the arc length, right? Okay, cool. So I want to relate how far I can see to how high up I am, and this angle is going to come into this somehow. So they tell me, thankfully they tell me the radius of the Earth, which is helpful, because that helps me figure out what this whole length is here, right? So the radius of the Earth, 3960 miles. And then they kind of, yeah, I remember this. Okay, they kind of step you through this thing. They want theta as a function of h. So they want theta equals something to do with h. All right, so they kind of step you through this, which is kind of nice, yeah.
What section is this?
Sorry, 6-4, yeah. So, I mean, what do you think we can do here? I mean, how do I say this? So let's remind ourselves of a few things. What's the formula for S? We know it's coming down a pike here. What's the formula for the arc length?
R theta.
R theta, cool. Alright. You have to know that for the test. Okay. Cool. So that's part B. I knew it was coming up eventually. So part B, they want theta as a function of arc length. Or the other one. S as a function of theta. So the higher up I get, what's going to happen to theta? I mean, they kind of give you an idea, kind of stepping you along from the first little picture of Earth and the second little picture, it got up higher. So if I go higher up, I can see farther out, so theta is going to get bigger, right? Because if I can see farther out, then theta is going to have to get a little bigger. How we go so far? What do you think? If I went forever out, or let me see, how do I say this? Would you ever be able to see the whole freaking Earth? Of course not. So what do you think the limit is? How much?
180.
Well, yeah, 180 total. So theta would be like 90, right? So that kind of makes sense. There's no way you could ever see the other half of the Earth from this side of it. That would be really freaky, right? That's gravitational lensing, the movie Paycheck. Have you ever seen that? We won't go there, sorry. So how in the world would these two be related? I mean, can you see an image? Can you see, what are we always looking for? We're always looking for, okay, put those two together. We're looking for right-angled triangles. Right triangles, there we go. We're looking for right triangles, because that's all we know for trig. Is there a right triangle in there somewhere? Yes, and in fact, it kind of makes sense that this point is determined by this being perpendicular to the surface. That's really the whole idea of this, is that as I look out, whatever's perpendicular to the surface, that's as far as I can see. So consider when you're standing on the beach, your height is determining how far out you can see. You take this until it's perpendicular to the surface of the Earth, and that's how far you can see. And you would think that you're not very tall, right, compared to the satellite's position. Compared to that, we're freaking ants. So how far out can we really see? That's kind of neat. You can actually figure it out from this problem. All right, so now that we know there's a right triangle here, this is what, this here I'm just going to call R. That's the radius of the Earth, of course, right? So what do I got in this? Let's draw that right triangle here. So this is going to be theta here. Is everybody cool with that? There's theta. What's this side? What's the hypotenuse? R plus H. Kick ass. I like it. And let's see, what else do I want? Oh, and what's this side? That's always useful. It's R again, right? So what relates theta with these two sides? Cosine. I love it. So cosine theta would be R over R plus H. R over R. And now comes the trick. Now comes what we just recently learned. What would kill cosine? No, definitely not. I understand why you think that, but I desperately, let me make this point really big right now. If I write this, that's bad. But that's why you guys think that secant would cancel cosine. It won't. So what you're thinking is 1 over secant theta times cosine theta. Not 1 over secant theta. What's secant theta times cosine theta? There's a problem that actually asks you about this. What's secant theta times cosine theta? 1. So that's not what I'm asking. I'm not saying, how do you make 1 out of this? What's the multiplicative inverse? I'm not asking that. I'm saying, how do you kill cosine so you're left with just theta? Yeah, the inverse cosine. The opposite function will do that. That's the whole purpose of having an inverse function, right? So if you take inverse cosine of both sides, what happens here? They cancel. That's what inverse functions do, right? So I get theta equals inverse cosine of... And R is not really a variable, right? Now I can go ahead and plug in what the value is. Theta is inverse cosine of 3960 over 3960 plus H. Is that the angle as a function of height? Yes, cool. So there you go. That's part A. That's plenty for me to do. You guys do the rest. At least now, I mean, you always, at least first, look for right triangles in the picture of what you're dealing with. You always look for that first. After we learn the rest of chapter 6, after this next test, then you can kind of do any kind of triangle you want to, but you still sort of look for right triangles because they're always going to be the easiest situation. If you don't have them, you're like, shit, I got to use the new stuff. Right? But you always look for right triangles because that's all you can deal with at the moment. And later, that's the easiest situation to be in. Maybe. All right, cool. So anything else from homework? Yeah.
What's your number 54 and 6.3?
6.3? 54?
Yeah.
Pencil mark in the book, it goes to number 55, but you need the information to do 54. It's kind of funny.
What's that? Sorry?
Exercises, it tells you when you're going and doing the exercise, like going through doing examples, it's like, go do 55, but you need that information to do 54. It doesn't matter.
Okay. So the formula you've got to use. So this one requires a little bit of reading. Right? And something you guys got to get used to starting this level at least is the fact that homework does not have to always exactly jive with any examples you've ever seen. Now, with that said, this is not that situation, right? what's the formula that I want to use for this? So I can have any triangle I want to. It doesn't have to be a right triangle. Yeah, this is A, this is B. I can't use 1/2 base times height because I don't know the height. All right, so let's just derive this. So nobody's read it, so we'll derive it. So here's theta, here's A, here's B, and I want to figure out the height of this thing, right? The area of this thing. So to derive the formula I want to use, I want to kind of fall back on stuff we've done in the past. So let me redraw this a little bit better. Let me see how I want to do it. Actually, yeah, let me just draw a better situation here. So whatever they give me the triangle looking as, I can always kind of reposition it so that one of them is on the base. Is that cool?
Yes.
You guys with me? Thank you. All right, sweet. Thanks, Franklin. Not to worry about myself. So to figure out this, I got the base. I wanted to make it A, just so it's not B, just to really confuse everybody. And I need the height still. So how do I get that height? When I draw the height in, what did it just create? Right triangle. It's crazy. So what relates these three things here? The angle with B and with H. What relates those three things? Yes, sine theta is H over B, because B is the hypotenuse, right? H is the y side. So which means that B I'm sorry, which one? I want the height. Sorry. H is H. Got it, Jeff. B sine theta. Cool. So the area of this triangle then, and this triangle is completely arbitrary. I could have drawn it in any way I wanted to, any side lengths, anything. I just have to know two sides and the angle between them. You with me? So an angle over there won't help me worth shit. I need the angle between the sides that I know. If I know that for any triangle, the area will always be this. You ready? It's going to be 1/2 the base, which is A, times the height, which is B sine theta. So that is the area of any triangle in the universe where I know two sides and the angle between those two sides. So now I just got to plug and chug. Right? So on number 54, they tell you the lengths are 7 and 9, and the included angle is 72. So you just put 7, 9, 72 degrees, and you go to town. Cool. All right. Is that cool? So the idea is pretty simple. I left it to you to kind of read it when you hit that homework problem. Don't only rely on your notes. That doesn't make any damn sense. Even if you're online and you don't have a textbook, you do have a textbook because there's an e-book online, right? So you can still go back and read the section like you should anyway. Okay, so now it's just plug and chug. There's a problem where they give you the area and you have to solve for theta, but now that we know inverse functions, that's going to be easy. If they give me A, big A, and little b, I can solve for theta. I'm going to just divide by this crap and then take an inverse sign, right, to get theta by itself. I can solve for the angle. Cool. All right. Okay. So I've squeezed all joy out of you. It's earlier in the semester than normal. Okay. I'm really getting efficient. You joke, Jeff, but it's true. All right. So kind of on the heels of that, was there anything else before we... Yeah?
Could we do 40 for 5.3?
Real quick, that the one kind of situation I didn't really talk about. So they factored the inside for you already. This one's going to be a little extra disgusting because what's the period going to be? Yeah, it's normally 2 pi, and now it's going to be over 3, because they already factored the inside, which is kind of nice. What's the phase shift going to be? Yeah, left 1, right? So -1 back, yeah, left 1. Do you guys see why this sucks? My phase shift is in terms of whole numbers, and my period is in terms of radians, right? In terms of pi. Does that, you see? So that's going to be kind of gross for figuring out the scale. I'm still going to leave that to you to figure out. All right, but I want to make sure that you understand. I don't know if this is the part. That's what you do at the very end, of course, right? Figure out what that is, and then just take your whole graph and go up 3. Just pick it up. All right. But did you have a specific question related to?
It was more of. It was actually concerning the fact that, you know, the periods and radians and the...
Oh, okay. Well, yeah. And I got to be careful how I say that. This still is radians, but it's just not pi, units of pi, right? It's not units of pi radians. So the one thing I would definitely allow when that happens is you can just estimate this as a decimal. So you can make it more related to this. Does that make sense? So since this is given to you in decimal form, right, there's no pi dependence, so they've already made that into a decimal. They just can't happen to come out to the nice decimal of 1. What is 2 pi over 3 about in decimal form? And then you can make your scale a lot easier. It's not going to be dependent on pi, it's going to be just real numbers, decimal numbers. Does that make sense?
Yeah.
Because trying to write that in terms of pi would be gross. Would be weird, actually. Pi divided by pi, which you can't really get anywhere with. Is that cool? You guys see that? Alright, so what I always try to do is, here I would have 3 pi there, so that the pi would cancel. So then you'll have everything in terms of numbers instead of in terms of pi. So I always try to make it match up. So that's not what's in your way of setting up the scale. Okay, so let's get back into 6.4. Look at that. It's like nobody's stepped in the snow yet. Yeah. Take a minute to figure that out. Oh yeah, good. Going to need to use your calculators for this. So what can you set up immediately from this situation? Gas. Of course, to get theta, yeah, so theta is the inverse sine. And when you plug that in your calculator, what do you get?
58.997.
58.997 degrees, obviously, right? Anybody do it in radians? It's going to be almost 1 radian, I think, if you do it right in my head. Nobody's taking me up on it. Sure.
1.02.
Hey, all right, 1.02 ratings. So be really, really careful about whenever you're talking about degrees, make sure you put the degrees symbol. Because if you don't see a degree symbol, it must be ratings. All right, so cool. That's one of the first things we can do. If I know side lengths, I can figure out the angle just by using the right trig function and the inverse trig, right? So that's one thing we can do with inverse trig functions. Now let me ask you this. If you saw tell me what you can about this. What is this? Tell me anything you can about that. It's got 3 letters. No, come on. It's written in purple.
You're gonna
Y equals 3 and X equals 7.
Sort of, maybe not necessarily, but it does tell you a representation of what it could be. This would be reduced. So I love it. I love it. You guys immediately went to the best thing to think about when you see this. Now one thing you think about is sort of like when I said logs or powers. So log of 3 is a power, specifically the power that 10 needs to become 3. Is that cool? So you always want to know what the output of a function represents physically. So what would the output of this function represent physically? This is one answer I would accept for what this is.
an angle.
An angle, I love it. You put an angle into a trig, so out of an inverse trig will come an angle. Because it switches the x and y. Is that cool? It switches the inputs and the outputs. So an inverse trig will always give you an angle. But what you guys said, a few of you guys said, was this actually relates to a triangle, where there's your angle, where who and what? What's going on? Y is 3, x is 7. 3 gaps. And why in the world does that make sense? And is that necessarily the triangle that it came from?
No.
No. It could have been 6 and 14. It's just that the ratio has to reduce to 3 over 7, right? But of course I'm going to do the freaking lowest terms. Leave me alone, right? So this, let me put these together. This represents an angle. I'm going to overanalyze this for a minute. How do I kill inverse tangent? Tangent, right? I was waiting to see if anyone said inverse tangent. That would be... It's like you need a radar detector. If you're a cop, you need a radar detector. Anyway. So this die, so I get tangent theta is 3 over 7. And if I gave you this problem, what's the first thing you would do? Hopefully you would draw the freaking triangle, because then it can answer any questions I ask you after that. Do you guys see? So if I said, for example, what's the cosine of theta? What would you have to do? Yeah, find that hypotenuse. So what would that be?
Good.
58. Cool. All right, it'd be 9 plus 49. All right, so then cosine theta is? Which is better known as? I like it. Cool. All right, bless you. Because you can't simplify square root of 58. You always take a second and see if you can simplify that radical. Right? Same thing as you shouldn't be comfortable with telling me the answer to something is 4 over 6. Something should hurt inside when you do that. So when you see a radical, if this was radical 56, 4 goes into it, it's reducible. That's what I call it. You can simplify the radical, you better do it. Alright, cool. I like it. This one, no. I can't reduce it, so screw it. I'm going to leave it like that. So now watch. Here's the question I'll ask you then. I'm not going to ask you all nice like that. I'm going to say find exact value for the secant of the inverse cotangent of 11 over 2. Yeah. That's pretty awesome. So what do? What did we just say that really means? I mean, you don't have to go through all this shit to get there. You just go directly there. What can I set up just by having that sitting there staring me in the face? A triangle. This is an angle. I know the sides have to be in this ratio for that angle in the triangle. So that expression by itself, I can represent it using a triangle. Now, let me say this. This triangle doesn't have to be anything physically real. It's just a representation of what this is. Because I might start putting some variables in here and people will say, there's no triangle that could... No, screw it. It's not a real triangle. It's just a representation of what this represents. I like that. Use the word more than once in a sense. I like. But where can I put 11 and where can I put 2?
11 is x.
Good. So this will be x over y for cotangent, right? Is that cool? So you guys notice something real quick while this is up there in your heads? Inverse cotangent of 11 over 2 is the same thing as the inverse tangent of 2 over 11. I mean, bam, right? So the reciprocation for the inverse takes place inside. That's kind of cool. Little thing just to store away, right? Just a little neat thing. So then how do I answer this question? Yeah, so for the secant I need... Yes, related to cosine I need the hypotenuse. Cool. Careful. Yeah, 125, yeah. Sorry. So 121 plus 4, kick-ass. Can you do anything with that? I love it. Yeah. 125's got 3 5s, so 2 of them come out as 1, and 1 of them has to stay inside. Poor dude. You draw straws. Figure out who that is. And then what's the secant going to be now? Yeah, look, because it's going to be the reciprocal of cosine. So cosine will be that over that. Secant's going to be that over this. Otherwise known as hypotenuse over the x side. You guys kind of with me? I mean, so it's funny that this looks very new and very different, but it's just a different way to write problems we've already done. You just got to realize what this represents. The immediate thing you can do when you see this is draw a triangle, because that's what it represents. I like it. Cool. So what if I gave you this here? Let's go to the next level. Find the exact value for... what you got, Jeff? Cotangent of the inverse sine of x over x plus 5. Bless you. Bless you. Bless you. You gotta be careful about stuff like x plus 5 squared is not x squared plus 25, stuff like that. My Calc 2 students do that, I cry. No tears come out. All right, so how do I build this triangle? What goes where?
X is the Y.
Yeah, the sine, the bottom is hypotenuse, right? And of course, x is the y side, just to make that interesting. So that would be related to sine. That ratio of those sides would be related to sine. So we see that. So that's an old skill we picked up, just a new way to have it in a question, right? Now to answer the cotangent, I have to figure out the x side, or a, whatever you call it. And that's going to be the square root of
5 squared.
10x plus 25.
minus x squared, I like it. So it'll be square root. X squared minus x squared is gone. You get 10x, I like it.
25.
Plus 25 to gas. So then this cotangent of that angle is, yeah, that thing
10x plus 25 over x.
to gas. And I really love it when they cancel the x's out. There's so many things wrong with that. I don't even know what to do. So don't do that. It's not too bad, right? Even when I throw variables in there, not bad. This year, specifically, this makes pretty decent physical sense. Why? Why, if I put a -5 here, why do you think some people would balk at that? What's got to be true about the hypotenuse in a physical triangle? It's got to be the biggest side, right? So if I put an x there and an x -5 there, then people are like, holy shit. But there's actually a little slice, a little domain piece where that would be fine. It would actually work. But people just take it at face value. Go, no, it can't be true. Yes, it can. Screw you. So then you just make the triangle. Yes, sir?
Can you show me how to use some parameter?
Which part? Oh, here? This here?
Yes.
So you foil this bad boy out, right?
Can you just take the square like that? In the square?
So, what's the square root of 5? Okay. What's the square root of 9 minus 4? Is it 9 minus 4, 5? So if you think that you can do what you just said, then you get answer of that as 1. So you're telling me square root of 5 is 1. Do you see that? So square roots are powers. They can't cross over subtraction and addition. I can't distribute it across those. So I can never take the square root of the parts of an addition and subtraction problem. Cool. That's another thing that I keep ragging on my Calc 2 students, but it just makes me crazy. So don't do that. Okay. Oh wait, good. Before I get too far away from this idea, so getting away from triangles for a second and just looking at trig functions as functions of real numbers. Right? They don't have to be related to any triangle. If I said solve this, first off, how do you know that at least one solution exists? What would I put here so that there's no solution? More than one or less than -1. Right? Negative numbers work fine. Sine goes from -1 to 1, right? So this tells me that there's a reason to do this problem. If there was a problem that said sine x equals 1.51, you could just immediately say, no solution, next. Right? So don't do work there. If you try to put in your calculator inverse sine of 1.51, it will say error, something wrong. Right? So how do I solve this equation?
Inverse sine.
Good. Look, inverse sine. See if anybody picks up on what I said earlier. If you do that and stop, you're wrong. So let me say, well, I won't say it. Well, if you give me that answer, don't worry. We'll get half of the answer. So what's half of the answer? Or part of the answer? What do you get for this?
0.535.
0.535?
Yeah.
Gotcha. And if you did it in degrees, what'd you get? 30? 0.66? 66? 63? All right. 30.7? I don't know what she is. All right. The book is always going to be nice at this point. Later, we're not going to be so nice. But right now, we're going to be nice. So what do I mean by that? What does an inverse sign always give me? What did I say when we first did inverse signs? Does it necessarily give me the right or the only answer? It gives me a reference angle. So this is a solution to this, but there are how many more answers to this? Infinitely many, because the sign keeps hitting the same values over and over. So how many times does sign to get this value? Here and here and here and holy shit, forever, right? So the book is going to do this for right now. Find all solutions in 0 to 2 pi. That's nice. So they cut it down there. Now, what's something about this that tells me why is there only 2 quadrants that are going to have answers, and what are those 2 quadrants? Not 4. Why 1 and 2? Because sign is positive, right? So I know this has got to be in quadrant 1 and quadrant 2. That's where my answers are going to be. The representative answer we got, which is an answer in its own right, that's an answer to this equation. That will make this work, is in quadrant 1. Doing the ratings. The other answer is going to be, where's 0.535 factor into the other answer? It's going to be the reference angle, right? I like it. So then this reference angle is 0.535. It's that much behind pi, right? So the other answer is going to be pi minus 0.535. Let me let you guys absorb that for a minute. Yes, sir.
I thought like the domain for sign was like negative 5.
Okay, cool. The immediate output of inverse sine will always be an angle that's in quadrant 1 or quadrant 4. That was true, right? Here's the answer that inverse sine gave me. Now, I am now looking to see, that's a reference angle. What other quadrant would I put that in so that it would make sense for this equation? Quadrant 2. So if this equation would have been, can you guys do this without the calculator? Let's see if you guys can do this without the calculator. Should be able to do that. Remarkably enough, you should be able to do that without the calculator. And then check it. Yeah, what will it be?
5 plus 0.51.
No. You can do it. You can do it. So instead of, this one was 0.535 because the sign had to be positive. And the answer to inverse sine has got to be first or fourth. Because it was positive, it came out in the first quadrant. So now that it's negative, it's going to come out in the fourth quadrant, being negative 0.535. Now try it. Do it in your calculator, see if you get that. You guys see that? So I really want this to make... I'm glad you brought that up, because that's not the point of that. The immediate answer you get has to be in one of those 2. Then the idea is it's a reference angle. And actually, sine's nice. Sine will give you the positive quadrant if it wants to be positive. It'll give you the negative if it wants to be negative. Which is nice. So now the answers to this are going to be in quadrant 4 and quadrant 3. The 2 areas where sine is negative. So now it's going to be that reference angle, 0.535. So it'll be pi, like somebody said earlier, but I wanted to catch up to you. Pi plus 0.535. Now it's got to be in the third quadrant down. You're coming to. Yes, sir.
So if we were to have this problem and we were writing both the solutions x2, we would just leave it like that? We wouldn't... The x2 answer, we would just leave it as pi minus 0.535?
Yeah, I see what you mean. You could, since this is a decimal approximation already, you could just go ahead and make it, approximate it. That's fine. You could leave it like this, or you could do like you're saying. At this point, there's no exactness to it anymore, because the 0.535 is already rounded off, right? So having the pi there's almost like, all right. But it's not wrong. But you can just plug it in your calculator and decimal for it. It's fine. Cool? All right. How do we feel about that idea? it kind of feels like how reference angles are supposed to operate. We're just sort of doing them in reverse. Because now I know the reference angle and I'm trying to put it into the right quadrant. Normally we find the right quadrant and we figure out the reference angle. This is kind of backwards. So what about... let's do one more of these. Yeah. We'll do something else. Same idea, find all solutions in 0 to 2 pi. While you guys are doing that, I'm going to pass out the practice test. Fingerprints on them for very authenticity purposes. Oh, this is Mr. Wallace. This is something. Yeah. If you want to know H, H is the Y side. That's the Y side. Yeah. So remember, the whole idea of how to set this triangle up is to this equals an angle. And when you take a sine on both sides, sine theta is this. So sine theta is y over h, and that's why that goes into y and that goes into h. The inverse part is what allows me to draw the triangle. The ratio is based on the sines. Yeah. The inverse can't like do double duty, flip it and yeah. It only tells you can make a triangle. Beautiful. First and go through this. Beautiful, because then you can take it a 180 over. Or even better, just go that by half. Cool. Oh yeah, good. We're going to talk about this later. All right, guys. So, of course, we should all be at the point where we go here at least. When you plug that in the calculator, what do you get?
1.04 rad. 1.04 radians.
1.04 rad or 59.5 degrees. And of course, you know, with the degrees, I'm going to ask you to do it in radians anyway, but the degrees you would just use 180 or whatever makes sense for the reference angle instead of pi, right? So what quadrants am I going to be in?
1 and 3.
Yeah, tangent is positive in 1 and 3 because it's a ratio of sine and cosine, so you be positive wherever they have the same sign. That's the first, third quadrant. So in the third quadrant, my reference angle is going to be this. So what's the other answer?
Pi plus.
Yeah, pi plus then, because I got to go this much past pi. Is that cool? You guys see that? And again, the more you understand reference angles by themselves, the more sense that's going to make, because it's just using reference angles like they're supposed to be used.
So if we did it in degrees, can we use 180 instead of...
Exactly. You do 180 plus this, and then you can write out what that is. Yeah, cool. And again, you can make this into a decimal if you want to. All right, so two things real quick. Actually, more than two things. On that first problem on the practice test, for example, somebody just asked me about it. So I'm going back to like real basics, A, B, C. But even beyond that, I'm kind of getting us ready for this idea. This is A, this is B, this is C, for example. Right, it's good old Pythagorean theorem setup. But across from A will be angle A. Across from B will be angle B. Across from C is angle C, which in this case is a right angle. So see, that's going to get us into the last two sections of chapter 6. Every triangle is going to be set up like this. So it's kind of nice. C goes with C, B goes with B.
I said, why?
Why not? Well, why don't we make C with A? Or something crazy?
Why don't you do different letters?
Because we don't like that. We like them to be more directly related. Yeah.
How come, so A would technically be Y instead of X? Or how would we determine?
Oh, it doesn't matter. I mean, remember, I can reorient this thing however I want to. So I could have put A there. It doesn't, remember, these are variables. So I don't care where you put them. If A is supposed to be 7 and you put a B there, guess what you're going to get when you solve for B? 7. So that side is 7. This side doesn't give a shit what you call it. I'm going to call you A. I'm going to call you B. At the end, you're both going to get 7 for that side, whatever you called it. So I like the question, but yeah, it doesn't matter as long as this is all my C stuff, right? That relates directly to Pythagorean theorem. Plus, Corin, I didn't mean to totally throw you off there, but there are theorems coming up where we use, they're just written in the sense that the sides are little a, little b, little c, and the angles are big A, big B, big C. So we want to make that connection quick. In theory, you can make them whatever the hell you want. Doesn't matter. Yeah. Another thing real quick. I'm getting way too many people telling me stuff like a reference angle. If you got a reference angle as this, what's wrong with that? It's not in the first quadrant, so you automatically know you made a mistake, right? Or you're not done. And normally when this happened would be, what do you got? Like if I said 11 pi over 4, what's the reference angle for that? Yeah, exactly. But do you see what somebody did? Maybe if I take a rotation off of this, to subtract 2 pi from this, I would get 3 pi over 4. But what are these angles known as? They are, starts with a C, coterminal. They both end at the same place. The other one just takes a full turnaround until it faces the same way, right? That's coterminal. That's not the reference angle yet. So this is not a bad idea, so it's a little easier to think about, but now you know in the second quadrant with the reference angle of pi over 4. So your reference angle has to be in the first quadrant. That's why you only have to memorize first quadrant values, because you're always going to take it back to the first quadrant. I like it. Cool. It's crazy how that goes together. Who remembers the idea of even and odd symmetry? Beautiful. So even is like x squared, which makes sense. It's an even power, so it's going to be something that's symmetric around the y-axis, right? Odd is going to be like x cubed. Again, odd power. It's going to be something that's actually symmetric through the origin. Whee! The check for this, if you remember this, was if f of negative x is f of x. If I plug a negative x in and I get the same output as an x would give me, that's even. Because it's mirror image across the y-axis. Even. If f of negative x equals negative f of x, odd. So, sine. Which one is sine? Is it even or odd? It's very obviously not even, or else it would be, right? Whatever sound it would be. It's definitely, it looks very cubic in the middle, sort of, right? So this is definitely, that is the same as that, goes through the origin. So that means that sine of negative x equals negative sine of x, because it's odd. Have we done so far? If I plug in, what's sine of pi over 2? What's sine of pi over 2? 1. What's sine of negative pi over 2? Negative 1. And then the negatives of each other, right? So sine of negative x is negative sine of x. Cosine, what is it? Odd or even? Even. It looks like an upside down parabola in the middle. Totally even. So cosine of negative x is just the same thing as cosine of x. Which only makes sense because if I ask you this angle versus that angle, cosine is going to be positive in both situations, right? Whereas that angle versus this angle, sine's going to be negative for the other piece. It actually changes this sign, SIGN. Okay, good. All right, that's everything I wanted to say. Damn. So tomorrow, we'll have review day. I'll have the answer key for that practice test. And we'll see how it goes. We'll see if I'm alone or if I have people in here with me.